Hello, I am Dr. Ahmed Abdelal, and today we are going to speak about the nature of sound. This is a class for speech, language, and hearing science. So we'll focus on Unit 1 that speaks about the physics of sound. And then in the upcoming units, we'll speak about the respiratory system, the phonatory system, and the articulatory system, articulation and resonance, the auditory system, and finally the the nervous system. Most of it is focuses on the central nervous system. So now let us begin to speak about the physics of sound as they relate to speech and hearing. So I'll go over some basic concepts. Most of them are clear-cut. You simply need to understand them all first, but then you need to memorize them. Acoustics is a branch of physics that focuses on the study of the production and the reception of sounds. And in addition to that, the effect that the sound makes on a receiver, like say the sound comes in, hits my eardrum, and my eardrum is going to jerk the ossicles or the little bones in my middle ear, and that is going to do this and that. So that is part of acoustics. The production, control, transmission, and so all of this has to do with the speaker or the source of the sound, producing a sound, controlling it, sending it out. And then the second two have to do with the listener, because we are going to focus on the listener in that case, who is us. So that has to do with the reception. The sound is there, someone receives it, and then what effect will it make on that receiver? If you take the word acoustics and just attach it to the word bio suffix or prefix, that means the sounds of living creatures. Bio means life. So the sounds that living things make. And that is the study of these sounds in the same way, and the production of the sounds and the perception of these sounds. But that includes all animals like birds, farm animals, whatever, including human beings. So, as you know, we use two systems. America here uses a system to weigh and to measure things, where we use miles, and we use pounds, and so on. We use inches. But the British system, which has become the international system, they use kilograms, they use kilometers. So the M stands for meters, and then kilometers and seconds. Meter, kilometer per second, because you are speaking about distance. And then that is for big units. For smaller distance, smaller units, then you have the centimeter, you have the gram, and you have the second. So a centimeter is, let me take it this way. A meter has 100 centimeters. A centi means 100. 100 centimeters are in a meter. A meter is a little bit, like 4 inches bigger than a yard. Kilometers. A kilometer is 1,000 meters. So centimeters make meters, meters make kilometers. and then grams make kilograms, and there's 1,000 grams in 1 kilogram. A kilogram equals 2.2 pounds. All right, so mass is defined as the amount of matter in an object or in a body. Body means object. So how much matter is there? How much, the elements, the earth is made of, say 120 elements, maybe 118, 120, something like that. So out of these elements, how much, for example, makes a particular object? And mass is usually, you always weigh mass. How much do you weigh? So that is weighed in grams and kilograms and tons. Density particularly refers to how much material is in, how the molecules are packed inside per square unit of volume. Let's say this is 1 square foot, for example. This container here, cube, let's say it's 1 square foot. And this is also 1 square foot. But which one is more dense? So which one has the material more packed into it? So on the left, you have a lot more molecules than on the right. Dense. Yes, things that are more dense will have more mass, will weigh more. Force is any influence that causes an object to undergo a change in speed, in direction, or in shape. So that is what force is. It is measured in newtons or in dynes. Newtons are for big things, big structures, like say a car, and the dyne is for very, very tiny objects like your eardrum. Your eardrum is the size of it is less than a dime. So 1 Newton is defined as a force that accelerates an 1 kilogram mass at a rate of 1 meter in 1 second. So let's say you have 2.2 pounds in a stone that is 2.2 pounds in your hand. You're going to take it and throw it, toss it to someone standing 3 feet away from you. Let's say that is 1 meter, roughly. So the force that you use to throw or to send that kilogram, that stone, you throw it to someone, that force that drives the object from your hand across 3 feet, that force that you put or that is required to transport the object, over 3 feet, that is 1 Newton. The 1 Newton equals 100,000 dynes. So we use newtons, like say, if you speak about a car, you're pushing a car, how much force do you put there, to move a car across let's say the car has 1,000 kilograms, and then you do the calculation, and then you move this car over 3 feet, for example, or over 1 meter. How many newtons did you need for that? So that is for big measurements. But a dyne is used for smaller measurements, and this is what we use in speech and hearing science, because we focus on the eardrum. It's a very tiny structure, and the air, as it comes in and it pushes it in, that is measured in dynes, because it's tiny, very, very tiny movements, very tiny amounts of force that are causing the eardrum to vibrate, and that again, cannot be measured in a big unit like Newton. Then volume is the space available inside of a container in 3 dimensions, from the top to the bottom, front to back, sideways. All that space that's available, 3-dimensional space available inside of a closed container that can be occupied by liquid, by solid, or by air, or any kind of gas, that is a volume. Sometimes we say, the amount of material that fits within that volume, sometimes it's called the volume, sometimes. But in reality, to be concretely focused on that concept, you focus on the space available inside in 3 dimensions where it can hold a particular amount, then you say that is the volume of the container. Speed is the distance that is traveled by an object in a given amount of time. So when you say speed, you say in like what time? So 60 miles, what do you mean 60 miles? An hour. 65 miles, and then immediately say the time. So that is speed. Velocity is like that, but it adds another point. Velocity is the distance that is traveled by an object in a given unit of time and in a specific direction from point A to Z. So that is the velocity, the speed and time and the direction. Then we move on to bigger concepts like Newton's first law, which is inertia. These laws are natural laws of physics. They existed since God created the universe. But it happened that Newton discovered how this law works, and he put words to describe it. So these words, you need to know them, understand them, but you also need to memorize them word by word, like the other concepts. So the law of inertia means that a body or an object, when we say body, it means a mass, something that has mass, an object or a human being, anything, a body that is in motion has a tendency to continue to move unless an external force interferes with it, unless it is acted upon by an external force that changes its direction or its speed. So things that are moving, they want to continue moving. Things that are still, that are not moving, they want to stay there unless something comes to shake them and make them fall or make them, Elasticity is an invisible force. You know how gravity is? You cannot see it, but you can feel it. Elasticity is the force that causes a deformed object to return to its original position or shape after it is deformed or after it is, distorted or taken away from its rest position. So when you have say an elastic rubber band, this is not an elastic rubber band, if you have one and you hold it like this, it is now at rest. This is how it is happy. This is how it wants to be. If you pluck it, take it away from rest, okay, then it will not be, it wants to come back to you. It will resist you as you keep pulling it away. It will resist you. The farther you pull it away, the greater the resistance, the greater the elastic force that wants to pull you back to the original position or which is the point, either equilibrium or point of rest for the object. So it's the force that causes a deformed structure to return to its original size. Like if you hold the ball and just squeeze it, make it smaller, it's gonna bounce back again because of elasticity, or the elastic force that brings it back to its original shape or size, or form or location, like the rubber band. When you pluck it, take it away, you let go, and that elastic force is what pulls it back to its original position. So when we speak about sound waves, in a sound wave, let's say it looks like, the wave looks like an inverted Z. So here's Z. You can begin a wave, you can kind of measure it from any point. So let's say rest here. You want to make a wave, so the air molecules are at rest in front of me. And I speak. So the air molecules will be pushed far away to the maximum point of displacement. As you push them far away, the elastic force that wants to bring them back will increase and increase and increase and increase. It will keep putting more resistance on them to slow their motion to bring them back again. And as they continue moving away from me, also inertia, the tendency for that thing is moving, it wants it to move, inertia will decrease. And then when you reach to the farthest point that the air molecules can go, based on how much energy I put in to make that wave, then it will go to a certain limit and it will not go anymore. At that point, that is called the maximum. Here, the maximum point of displacement. Here, elasticity is at the highest point and inertia is at the lowest point. The thing just completely stops. It can't move again. So then, the air molecule is going to bounce back again to me, because elasticity, the elastic force that brings the rubber band back to the midline is the same. It will bring the air molecules back again to the point of rest. Will go back to rest. But when they come back to rest, as they come back, in the elastic force, it becomes less and less and less and less resistance. When it comes to the original point, which is near me, it is not going to stop there, because inertia, now the thing started to move again. So elasticity decreases and inertia increases and increases and increases and builds up the closer you go to the original point. As it comes to the rest area, well, it figures that there is no resistance from the elastic force. Elastic force is at zero. So inertia says, since you are moving, continue moving, get away. And it slips by the rest area, and it swings on the other side. And it travels an equal distance, as you could see, comes to rest, goes back on the opposite side, now, and then goes back again to rest. So that makes one complete cycle. From rest, one compression, because you are applying force here, pulling the thing away or pushing it away. That is compression. And they'll explain more about it. And then the molecules are going to bounce back again to rest. But because inertia decreases, then the molecules continue to bounce back past the point of rest. And then the same thing again happens. As you go away from the midline or rest, elasticity increases, inertia decreases, the molecules stop. And then they will be swung back again, because of elasticity will start to move it to the point of rest again. And then as it's moving, elasticity becomes less and less and less, and the inertia builds up more and more and more. So because of less resistance at this point, then inertia will say, continue, keep going, keep going, keep going. And then it pushes to the other side. So we call this side that's on top of the line, we call it compression, because you're applying force. It's like 10 people are standing in line. You come from the back and just push someone. You push the last one. That last one has 1 foot. Every one of them has 1 foot distance between them. And then so you push one, and then that person will be shoved against the person in front of him or her. So they collide. That will be compression. You compress that, last person in line. You pushed him away by 1 foot. So when he hits the person in front of him. Then at that point, 2 things happen. That person who is pushed and he pushes the second one in front of him. That second one is gonna be pushed 1 foot forward. At the same time, the one who pushed him will bounce back, goes back 1 foot back to where he was. So now you got this person went back to where he was. That is 1 foot gained again. And the other one is gonna leave his space and go out 1 foot. So instead of a distance that is 1 foot between them, that compression, that distorted things, that compression is always followed by one rarefaction, where when the molecules collide, each one leads in the opposite direction and they create a gap in between them. That is rarefaction. So rarefaction has less air molecules. It is produced basically by force that you really did not apply. It is by forces of nature. So elasticity and inertia are responsible for making that wave going back and forth. So we'll explain that more after we look at these concepts. Energy is the element that enables work to happen. Like you say, gasoline is energy. Gasoline in general terms. Coal is energy. If you take it and burn it, it will give you energy. So it is a substance that will enable you to produce work. But you may be using it, you might not be using it. It's just as a concept. Potential energy is energy you have, but you are not using. It's if you need it, you'll use it. Like you have gasoline in your car. The car is parked in the garage. Now you have the gasoline in it is full tank. Well, we know that full tank might make your car run 300 miles. So that is potential energy. If you want, it is there, but you might not be using it. You are not using it. It is stored. It's like this, say, boulder, and you keep pushing it up. You are giving it energy. You are loading it. When you bring it to the top of the hill and you just kind of push it a little bit, it will go down its gradient. It will roll down with no energy, with no force or energy that you put into it, because you are going to get back the energy that you put as you were pushing it up there. You get it back because the object then rolls down its natural gradient. Kinetic energy. Kinetic comes from kinesis or movement. Kinetic energy is the actual energy that is used in order to produce motion. So, for example, calories, like say calories that you consume or burn in order to to produce a particular, set of movements, for example. Power is the rate of energy that is used or the work that is produced in a given period of time, and that is measured in watts. So, for example, you say in 1 hour, how much does this lamp, or does this, this lamp, how much does it, what is the rate of energy burning or energy consumption for this light when I put it on? So I say in 1 hour, it will consume 40 watts or 70 watts in 1 hour. So you put the time limit, and then you put the amount, the rate of the energy that is used in order to give you that in the particular period of time. And it is measured in watts. Watts is the name of a scientist who discovered the measurement. Then we speak about intensity and about pressure. So intensity is the power per units of area. So you say, for example, I have the eardrum, and there is air pressure coming onto it. That air pressure, how much force is it exerting on my eardrum, pushing it in? How much? And then you say, well, the surface is 0.55 of a centimeter. And then that force that is coming in, you kind of have an equation where you divide this by that, and you find out the amount, the intensity. So it is measured in watts per square meters or in watts per square centimeters, like the eardrum, 0.055 a square of centimeter, I mean. So then pressure is the force that acts perpendicularly, like in a 90-degree kind of surface, on a surface of an object. It is measured in pascals or in dynes. Pascals are for the bigger elements, for bigger things, and dynes or microbars for smaller areas like the eardrum, for example. So we always use the smaller measurements for our purposes. So also the pressure can be measured in centimeters of mercury or centimeters of water, H2O or Hg. Hg means mercury or H2O. So simply, if you get just Google nasometer or manometer, and you will find how they, for example, they have a tube. So the tube is curved like this, and it has water in it here and here. And then it has on one side, you have a pipe and you blow. When you blow, your breath, your pressure from air pressure, is going to move the water or the mercury from this side to and up. It makes it rise. And then you say, how many centimeters of water were you able to displace with your breath? How many centimeters of mercury were you able to displace with your breath, with your pressure? So, for speech purposes, listen to this carefully. The smallest or the minimum amount of pressure to make the smallest speech sound is 3 to 5 millimeters of water or millimeters of mercury, the same. So 3 to 5 centimeters H2O. That is the minimum amount of pressure needed to produce the smallest speech sound. So we do not, when we speak, we do not just whisper to ourselves or to others. We want to make speech that is much louder. So for speech purposes, the amount of pressure that is required to make normal conversational speech goes from 7 to 10 centimeters H2O or centimeters Hg. Okay? So that is an important difference. And again, you could Google manometer, and you will find how this works. Okay, let's look now at sound. You hear the arid philosophical argument that some people sometimes would like throw and say, if you are not in a forest and the tree falls, does it make a sound? That is a completely absurd argument. When you look at the definition, scientific definition of a sound, you definitely will be able to answer that silly question. So focus on the word audible. A sound is defined as a sound is an audible disturbance in a medium. The medium can be air, can be water, it can be gas, it can be across a wire. So it is an audible disturbance in a medium. So when the tree falls, as it falls and hits the ground, it is going to disturb the air, and the air is going to keep going up and down and making that noise that will show us that the tree has fallen. Now, if you are there, that makes a sound. If you are not there, that makes a sound. Okay? Because the word here is audible. Audible means possible to hear. Like, if you were there, you will be able to hear the sound. But the fact that you are not there, well, the tree makes an audible sound. If you are there, you'll hear it. If you aren't, the sound is still there. So, I mean, really, these arguments. So, the disturbance, it disturbs the normal flow of things. Like you say, you see a lake on a quiet day and you look at the surface, it is so smooth and so still, no motion. The water surface is just no movement. And then you take a stone and just throw it, and then you start to make ripples. The water is going to just lift up and go up, and this is going to continue to expand and expand and expand until finally it dies down. That's similar to a sound wave. So the disturbance, when we speak, we push air molecules away, and they compress against other molecules. They literally rise as they collide and then go down, come back. So disturbance is what makes sounds. So the sound is a result of the disturbance that changes normal air pressure. So when we speak about pressure, we say atmospheric pressure. Atmospheric means pressure in the atmosphere. The French labeled it as P atmos, pressure atmospheric. So that is the symbol that they use sometimes in physics, atmospheric pressure. That pressure is the air pressure outside or inside, but you measure it because, as you know, air is made of, like what we say, things that are floating around us and covering us, oxygen, nitrogen, and so on. And they put weight on us as well. So Atmospheric pressure is the pressure that is measured at sea level and at freezing temperature. Okay, sea level and freezing temperature. That is atmospheric pressure. And then there is, if the pressure is less than atmospheric pressure, we call it negative pressure. Sorry. If the pressure is above atmospheric pressure, we call it positive pressure, means higher pressure. Means there's more weight, more the air molecules are, more, there are more of them and weighing on us. Because when the temperature increases, air molecules, instead of huddling and becoming closer to each other and closer to the surface, when you heat and the temperature increases, they want more distance, and then they rise, and that makes the pressure less. So this is why you notice for air conditioning, you have the vents above near the ceiling or higher, because cooler air sinks down, comes to you. Hotter air rises, and this is why you have the heating vents near the floor or on the floor. So generally, negative pressure is going to create suction because there's not enough air in there, and if the air always wants to jump in to fill in. If there's an area that doesn't have enough air from all around will just force itself, will jump into complete to fill that. So negative pressure creates suction. Air is affected, as I mentioned, by the temperature, and every layer, the ground, or there's a surface on a lake or something, you're going to always have columns of air that create currents that are the same temperature, that are flowing in the same way. So you might have like one area that has cooler, and then above it you have maybe warmer, and above it you have a little bit, warm, much warmer, and so on. The movement of the air in, let's say you have a room that has no windows and you close the door really kind of sound insulated. So there's air in the room. The air will be moving, constantly moving, but it will be moving in a predictable way, in a steady manner, at a steady speed. That is called laminar flow. Okay, moving in a systematic way, no waves, like in a lake, the molecules of water in the lake, there's no wind, and the surface of the lake is just very, very still. The molecules are moving, but in a very steady, very, systematic manner. So we use laminar flow to create vowel sounds, like e, they require, laminar flow. So always vowel sounds are created with that. But if we want to make consonant sounds, we have to make an obstruction to create turbulence. You create eddies and waves, like throwing a rock in the water. It disturbs that. That disturbance becomes waves. In the air, when you speak, your muscles, vocal folds vibrate. The vibration displaces the air inside of your throat, and the air comes out of your mouth and displaces the air that is outside of your, of your body, and then it continues to do that wave until you reach a point where your sound cannot be heard, and the end, like behind you, in front of. So your sound at some point will not be heard because the energy just dissipates or becomes dampened. So all consonant sounds are produced by turbulent flow. So by disturbance to the normal flow of air. So now we're going to speak about Boyle's law. Things will make more sense later when we speak about respiration and how Boyle's law relates to respiration. Boyle's law, you need to understand it well. You really need to memorize the words that it says and see how it applies to respiration. So listen, every single word of that means something. If you take a single word out, that doesn't become Boyle's law. Okay? So if you take the word enclosed out, and I just put it bold, made it clear, if you take it out, that doesn't become Boyle's law. Boyle studied so many years to finally figure this out and understand it, and you put it in just in a couple of sentences, and that's it. So he says, as the volume of a particular enclosed space. Okay, so that you have a container, and that container is enclosed. No air comes into it, no air goes out of it. Okay, as the volume of an enclosed container increases. How do you increase a volume of you have a container that is sealed already. How do you increase its volume? So let me give you an idea. So you have, say, like a syringe. The syringe, if you put your finger or your thumb on it and close it, and then pull the handle down, you are going to expand the volume without adding air into it. But what will happen? You let go of the pump will be sucked back in. So this is like this. You have a container here that there's a pump here, and there is, in that container, let's say you come to, say, 4 inches here. And that container has like this number of molecules. You count them, you will find them the same as here. So what you did, you keep the temperature the same, no change in the temperature, 300, 300. Now the air is here, you shut down this, there's no air coming in, there's no air going out. So you have a container with this number of molecules, air molecules in it. So you push down from 4, you go to 2, or to 3, you push that down to 3. You made the volume here smaller with the same pump. But what did you do? You added pressure because you compressed all of these molecules into a smaller space. So you increased the pressure. Increasing pressure means crowding the molecules. But then you take back, you pull the handle up to 4, now you increase the volume again. And the same molecules are there, but they have more space to go around, to go and move around. So now you increase the volume and they created less pressure. Okay, you decrease the volume, you create greater pressure. But given that the temperature is the same, because if you increase the heat, that will affect the pressure, will increase the pressure no matter what. So you have, this is why I'm saying you have to really watch out for every single word. And if you don't say enclosed container, your whole Boyle's law is useless. It doesn't become Boyle's law again. So enclosed. What he did with this, he got a big truck and closed it all over the place. And then he put water in it, and under the water he added heat, and that increased the pressure in that container. Adding heat, and the thing was closed, and that increased the pressure. So what did he do? He made a hole in back of that big container with wheels, and then as the pressure was released, it pushed that car on the opposite side. He made rails for it, and he created the steam engine. So that is where the law, Boyle's law, is, and this is how he recorded his invention of the steam engine, because he discovered this law. So it says again, as the volume of a particular enclosed space increases, as that volume increases, you have less pressure. The air pressure in that same container decreases. You just, some areas like a conference room might have a wall in between. So that wall, you can push it back by 3 feet, you expand the room. Or you can push it in by 3 feet, you can narrow that room. So you have, if you increase the volume, you have less crowding, you have less air pressure. And if you decrease the volume, you are going to have greater pressure. It doesn't work the opposite way. Do not reverse it. So it has to be the volume that increases and decreases, okay? I don't want to confuse you, but you have to begin with the volume. If the volume goes this way, then the pressure goes the other way, okay? It doesn't go the other way around. So we say, since they are opposite, one goes down, one goes up, we say they have an inverse relationship. They are inversely related. So you could see now, here in motion, that relationship. Here's the same container, and at 4. And then when you compress, you decrease the volume, you increase the pressure, and you look at, see here, and you push, the pressure this way increases. And you can predict it, you can measure it. Every little bit of movement here is going to produce a movement here, and it is predictable, it is measured systematically manner that you can predict and say, okay, the handle down to 3, the pressure is going to be here, is going to be this level. There's no guessing about it. So it is systematic, it is measurable, and it is predictable. If you do it anywhere in the world, it will be the same way. So that is the relationship between pressure and volume. And the same thing we take then and we apply to the lungs. So your lungs are containers like this inside of your chest, and you expand them in order to draw air, to create negative pressure inside of the lungs. And that negative pressure will create suction, and that suction will suck the air from outside, and the air continues to flow until the pressure inside the lungs equals the pressure outside. You reverse the same thing. After you inhale, your muscles relax, your thorax comes down, diaphragm rises, the abdominal muscles comes in. There pressure on the lungs from all directions. That is going to make them smaller, compress them, and that will increase the pressure. And that increased pressure will force the air out of the lungs into the oral cavity or nasal cavity. So this is how this law relates to respiration. For compression, think about it. I explained it to you and how you saw the sound wave. But now look, let's say I'll put the cursor here. Now I'm going to bring it here. Okay, and a little bit back. No, so I don't know if the cursor is actually, no. But so here is that distance between the cursor and the last molecule in line. It hits and it comes back again. the same distance. Between it and the one before it, when it is being displaced, there's a distance that keeps repeated among all of them. So that means the air molecules near me, when my vocal folds push the air, that is called compression. There's a column of air here, and there's another column next to me. So my muscles then, as the air pressure coming out of my mouth is going to push the air out, all of a sudden it makes it collide, hit. Now there's no space between the molecules. That is compression. So compression is an area of increased pressure or positive pressure resulting from the collision of air molecules. That immediately is followed by rarefaction, by emptying an area that is empty, an area that has less. It doesn't mean it's completely empty, but it has less air molecules. So as the two collide at the very same millisecond, the one that is hit is going to bounce forward, and the one that was the original one that hit it is going to bounce back again to where it was. And instead of having a normal distance between them, let's say 1 foot, now you have 1 foot created by this one going back and 1 foot created by this one going forward, just for a little brief period of time. And then things go back again to where they were. So that is repeated. Each one is going to do the same, like, hit and go back, hit and go back. So, and the wave, you have a peak that represents compression, and then the trough, or the area that's going below the line, that is rarefaction. And the sound wave is made out of compression, rarefaction, compression, rarefaction, compression, always alternating. You see, compression, rarefaction, compression, rarefaction, and they just keep repeating themselves. Now here, on one end, you have your eardrum, for example. The air is coming in. Red means compression. The vertical bars the blue bars mean rarefaction. So now the compression, first you go compressing your eardrum, and then your eardrum bounces back out, and then it is compressed back in. So it keeps constantly going back and in and out. That is vibration. It is taking the sound wave and translating it into a mechanical wave, mechanical energy. So now we look at Hooke's law, and we look at how the forces of inertia, elasticity, and friction, how they interact together to create a cycle, to make it keep going. So let's take an example. Here's a wall, here's a table, and on the table is, let's say, a piece of wood or metal, and then you maybe you can put next to it a ruler, and you go to the arrow. Naturally, you put the arrow close to B. So you tie this with a spring to the wall. When you push, this is how the thing was resting at like B. If you take this piece and just pull it back, bring the arrow to the C and let go, what will happen? How do these things interact? So when you pull, I'm asking you the question, when you pull the piece of metal out to the sea, do you increase or do you decrease elasticity, the elastic force? Okay, you need to answer the question for yourself. And now, do you increase or do you decrease inertia? Because they are opposite. If one increases, the other decreases. So you pull this back, and you bring this arrow next to the C. And then when you let go, will that piece of metal bounce back to the level of the B and stop, or will cross and keep going until it reaches the A and then bounces back again to rest and cross again over to the other side. And it keeps doing this until it comes to a halt and stops completely. So that's how exactly the air molecules behave. So inertia works the opposite direction and the opposite manner of elasticity, and friction is caused by air resistance, and that dampens or causes the energy to dissipate. So what does Hooke's law say? Hooke's law explains the relationship between elasticity and inertia. So here's someone holding an elastic rubber band, and he pulls or she pulls it away. As she pulls it away, the farther she goes, the greater the resistance, the greater the elastic force that wants to bring back the elastic rubber band to its rest. It doesn't want it to be stretched. So the farther away that you pull, the greater the elastic force and the less the inertia. So now we stop at this point here, and that brings inertia to zero. It brings that thing to the maximum point of displacement where it was stopped. That's the maximum point of displacement. And the elastic force reaches its maximum limit. So when we let go, the elastic force is gonna pull back the object toward rest, but as it keeps pulling it back to rest, the elastic force decreases and inertia increases. Now the thing is moving back, and the inertia wants it to continue moving. When you come to the point of rest, it will say, well, there's no resistance here anymore. There's no elastic force. So why not continue moving to the other side? So if this person lets the rubber band go, it is not going to stop here. It will bounce on the opposite side. So then it will keep going away, going until it reaches a point of maximum displacement on the other side. And then it keeps repeating this, but every time it is going to lose some of that energy because of friction, because of damping. And then the movements, the waves become smaller and smaller until the thing stops on its own. So Hooke's law says, it describes the elasticity rules. It says the degree of elastic force is proportional to the distance of displacement. Means the greater the distance of displacement is, the more you pull that object, the greater the elastic force will be. It's like taking a bow and arrow. The farther you pull back, the more that you load it. And so when you let go, it is going to just, you have greater force loaded because of the elastic force becoming greater. So the degree of elastic force is proportional to the distance of displacement and acts in the opposite direction. So in the opposite direction of the pulling or the displacement. So the person is displacing that in this direction. But the elastic force wants to pull back in the opposite direction. Okay, so this is Hooke's law. And what is the role of inertia? Friction. Friction says means once you let the object move on its own, then it will be stopped by the friction or resistance of air molecules, and that will make it dampened. Okay, so let's look here now. Here's a pendulum. We use a pendulum even though we do not hear the sound waves a pendulum makes. Only if a pendulum makes 20 movements, 20 cycles in 1 second, sound is always measured in a second. If you do not make at least 20 vibrations in 1 second, the human ear cannot hear that. Given that your hearing is is good, you cannot hear a sound unless it is 20 hertz, 20 vibrations in 1 second. So the experiment you make with the pendulum, please don't come and say, oh, the pendulum makes a sound. No, this is to simply help you see with your eyes what you could not see in the sound. Because the sound, how do you understand this? So there's nothing there, but you hear it. So we use like basic concepts. We make you try to understand. We use objects to demonstrate for you. But here we are not speaking about the sound that it makes. We are speaking about the movement and how this pendulum shows you how the air molecules move. So first, when you displace the pendulum from its rest, as you keep going up, you have greater elastic force. You have less inertia. And then you let go, then you reach a maximum displacement point. You let go. Then elasticity is going to swing the pendulum back. As it keeps going back, elasticity decreases and decreases, but inertia increases and increases. At the point of rest, elasticity is at the zero. There is no resistance, but inertia is at the maximum level. So that is going to make it overpower the object, and it's going to swing it, it will allow it to swing freely to the other side. And it will keep going. Then from that moment on, elasticity will increase and it will pull back the object. But every time, because of damping or because of the resistance from the air, then that object, the pendulum, cannot go the full distance. Every time it decreases by a certain amount or a certain, kind of little bit every every cycle systematically decreases a little bit until you come to a point, then the thing stops. So the waves themselves become smaller and smaller and smaller, even though they are periodic. You can predict them. They start big, but they become smaller at the end. But you can calculate them, and they're systematically decreasing in a pattern. So you need to understand Hooke's law. You need to understand how Hooke's law enables a cycle of vibration or creates a cycle of vibration and makes the vibration continue. This is an exam question. You need to really understand how to explain it. So here it is again. It is demonstrated here again the same way I explained with the arrows. As you go from rest, you increase elasticity, you start, then go to maximum point of displacement here. That means the greater the peak is, the greater the amount of energy that you put into it. We later understand this as loudness, okay? Because it has to do with the energy that you put to make the sound wave. Then the thing, after the point of displacement maximum, then as it goes back to rest, you have increasing inertia and decreasing elasticity. Then you reach rest, zero elasticity and maximum inertia, and that will allow it to swing to the opposite side. As it keeps going, elasticity will increase, and then it will prevent the thing from moving farther than this point. And then inertia will stop and elasticity will be at the maximum limit. Then it will repeat the same cycle again. However, because of the loss of energy because of friction or damping, that's going to make these cycles smaller and smaller every time they keep swinging. So you will have the pattern that we described here. So you need to know how to describe this and understand it really well. So amplitude is the same. Amplitude is another way to describe the maximum point of displacement. And we come to know that this same amplitude, how we understand it, it is a measure, it tells you how much energy, how much intensity is there to make that sound wave. And then we come to say this is a decibel, this is the level of loudness. Damping is the decrease in amplitude, the decrease in the distance of displacement because of the effect of friction. The sound wave, when you make a sound, it doesn't just go like an arrow away from you and it just, no, it goes like a globe around you. The sound travels behind you, in front of you, right and left, up and down. In 3 dimensions, it will travel. But the maximum pressure that it will put on, if someone is straight right 90 degrees across from you in a classroom or somewhere 90 degrees, that person will get the loudest sound that you make. Someone who's sitting behind you at a 90 degrees, they will get the sound louder than anyone else. So as you keep the angle changes, then the sound becomes less and less and less, and when you come to your sides here, it becomes the weakest because of the center of pressure. But just keep in mind that sound wave is like a globe around, it goes in all directions. So it is like this. Again, the air molecules are being compressed. They hit columns of molecules in front of them. They hit them, collide, and then they bounce back. And the ones that are hit repeat the same thing. They hit another column and come back. And you keep going. So at the very far end, the last row of molecules is going to be pushed out and then come back in. Beyond that, they don't do anything else. So the outer edges of that globe, the outer edges of the wave are called the wave front, the point after which the sound wave cannot be heard. Okay, the wave front. So a sound wave, again, is a disturbance in pressure, like air pressure disturbance, that moves through a medium. That medium can be water, it can be air, gas. We use, because of our verbal language, we focus more on air. A wave front is the outermost area of the sphere of the sound wave, after which the sound cannot be heard. So the acoustic energy of the wave diminishes by a factor of 1 divided by the distance squared. So if you want to say that every foot I go, you say 1 divided by 1 square foot. And you keep going, and every time you move 1 foot, that is going to be less and less and less and less and less, and then at some point, there is no more. That energy is dead. The sound can't be heard. Okay, so one way to help us understand how sounds are made, we say that explain how sounds are made by simple harmonic motion. E-harmony, you have heard, harmony means a systematic pattern that happens in a predictable way, like a pendulum. You swing a pendulum, it goes, he's at rest. You go, you let go, and it keeps swinging back and forth until it makes very tiny cycles and then it stops. So you can predict that. A simple harmonic motion is a motion that occurs in a predictable pattern. Pattern means you can predict it. It's going to happen in a systematic way. If I go and say A, B, Z, X, Y, and then again A, B, Z, X, Y. So every time you make, the pattern repeats itself. The most important requirement to produce simple harmonic motion, like the movement of the swing, the movement of a pendulum, the movement of a guitar string, the most important requirement is that the elastic force of the moving object is proportional to the degree of displacement of the object. So it means if you pull 1 millimeter, elasticity will increase by 1 unit, for example. If you pull 2, then elasticity will increase by 2. 3, as you systematically increase the distance, the elastic force will increase in a predictable way. In a particular unit, it will keep increasing in the same way. So that elastic force of the moving object is proportional to the degree of displacement of that object. Then that elastic force works in the opposite direction of the movement of the object, as we explained when we explained Hooke's law. So here there are some more concepts that, as now we look at the property of the sound waves, and we look at how frequently they occur, and the relationship between one single sound wave and the group of sound waves. When you speak about sound waves, all the time, you can only measure them in 1 single second. So the human being